Hey everybody, this is Trigonometry at College of the Sequoias, Math 154 as we know it here. This is our fourth lesson. It's section 5.4 in our book. It might be different in your book if you attend a different college or use a different instructor, but this is really word problems and examples using degrees. So section 5.4, ooh, that's a dark blue right there. All right. Maybe not. Yeah, it is. We're looking at word problems and examples using degrees. Okay, so let's remind you about some stuff. Let's say, for example, we have a rectangle. And I don't know how big you want the rectangle to be. Let's say it's in your backyard. It's a garden area. It's 12 feet by 10 feet. And we want to find the cross diagonal distance. This distance is how they describe TV sizes. So when you see a 55 inch, it's 55 inch along the diagonal. So we've got a box. And it's a little bit longer than it is wide. This is 12 feet. This is 10 feet. And we're looking for this distance here. Okay? That's what we're doing. Well, look, we've got a triangle. So we've got good old a squared plus b squared equals c squared. 12 squared plus 10 squared equals c squared. 144 plus 100 equals c squared, which is 244. So c equals the square root of 244. Okay. And that's not really all that helpful to most people. So let's just find the square root of 244. And my calculator is showing all this. So 15.62049935. That's a lot. That's a lot of numbers. And I bet if I multiply by like a million, it'll show me all the next few numbers. So that leads me to a question. How many digits should I include? Okay. Well, this is all the answer is actually dependent on some information. It depends. Do I know that the 12 feet above was equal to 12.0000? Like there was no rounding? Or did we round to 12? Was it 11.98? And we just said it's close enough to 12, we rounded. So that leads us to the, go ahead and pause it real quick. Finish writing it down. This leads to the idea of significant digits. Significant digits. And there's some rules about it. When you don't know if the value has been rounded or not, you kind of need to assume it has been. And the idea behind this is the answer or the result can't be more accurate than the starting information. More accurate or precise than the starting data. Okay. So oftentimes, how do we get this data? The data is initially obtained through measurement. And the number of digits obtained during the measurement are called significant digits. They are significant. So the official name is significant digits. Some people say sig figs, like significant figures, because it flows a heck of a lot easier, rolls off the tongue. So what are the rules behind this? So there's some rules. Number one, all non-zero numbers and any zeros between them are significant. You'll notice my Z's, I always put this little crossbar in them. If I don't, they look like 2s. So that's a Z. So some examples. We've got like 602, 94.1, 5,000,001. There are 3 digits here. We count the 0 because it's between it. 3 here, 7 here. Okay. Then we look at, those are just basics. So now let's do some more stuff with it. Hit pause if you need to. So we have part 2. If it's before the decimal point, and I'm going to abbreviate decimal point DP for this lecture because I have to use it a few times. Zeros that occur at the end of the number could be there from rounding, so we will assume they are insignificant. That's important, the insignificant part, unless stated otherwise. Commonly, they show significance. Common way to show zeros are significant is by putting the decimal point in. Okay. So for example, we've got 250 and we've got 250 point. 1, 2, that's a 0 at the end of the number. There are 2 significant digits here. 1, 2, the 0, the decimal point tells us the 0 is part of it. There's 3 here. And it's important that it's not part of like a text. This can't be the period at the end of a sentence. From a sentence. Okay. And then we have after the decimal point. Maybe I'll go to a new page. I'll pause. Let you guys write this. Because this is the part where it gets the most complex. So 3 after the decimal point. If zeros are shown at the end, they are significant, which is different than if it's before the decimal point. If they are after the decimal point, but before any or before all non-zero numbers, they are not significant. So I'll show you what I mean. It's easier to see just written out. For example, we could have 49.2 or 49.20000. Here there's 3. Here there's 1, 2, 3, 4, 5, 6, 7. We include the zeros at the end because they indicate precision during measurement. Measuring. No one writes extra zeros unless they need to. So the only reason to write extra zeros is to indicate, you know for certain it's not 49.2 rounded. You've got those extra zeros. And then the other way is if they're before the decimal point. Uh, 0.00492 and 0.0049200. Here, these are the non-zeros. Zeros in front don't count. There's only 3. These are our non-zeros, and we include the ones after. We don't count those. So we got 3 and 2. There's 5 here. Now, if the number's got something in front of it, they're all included. here we got to include them all. 1, 2, 3, 4, 5, 6, because these zeros, according to rule number 1, are between non-zero numbers. That's 6. It's important to know how they work. I'm not going to be a big stickler on it, but when you start doing science classes and engineering and stuff like that, those digits matter, and you need to know how to do them, okay? Pause it if you need it. The show goes on. Let's look at solving some triangles. So here we want to find the measure of all sides and angles. So in our first example, let's draw a pretty triangle. We're going to make it a right triangle. We'll call that angle A, angle B, angle C, which makes the opposite sides the lowercase letters. Lowercase c and capital C look the same. That kind of sucks. And what we know that angle B is 52 degrees, 30 minutes. And we know side C is 14.2 inches. So that's 52 degrees, 30 minutes. That's 14.2 inches. What can we do? Well, starting off, let's make a little table. What do we want to find out? ABC, ABC. We do this a lot in later chapters where the triangles get difficult. And we know this is 52 degrees, 30 minutes. And we know this is 14.2 inches. What else do we know? We have one more piece of information, actually. C, by being a right angle, is 90 degrees. So the easiest thing we can actually start off with is finding angle A. We know this angles in a triangle have to add up to 180. 52 degrees, 30 minutes as a decimal is 52.5. I subtract the 90 over. I got 90 on the right side. I subtract 52.5. What do I get left with? 90 minus 52.5 is 37.5. Does that sound about right? And since it was originally written in minutes, I'm going to write it in minutes. 37 degrees, oops. 37 degrees, 30 minutes. There we go. Ignore that screw up. Now we need to find side A and B. Well, I have this piece, I have angle B. What options do I have? I have SOHCAHTOA. These are my options. And we want to use angle B because that's the one that's given with. In this case, we know angle A is accurate. We didn't have to round it because we didn't use a calculator. There was no decimal places. But we're going to use angle B. So which one applies here? If I want to find A, finding side A. Side A for angle B Side A is adjacent. Right? And side C is the hypotenuse. So we have adjacent, we have hypotenuse, we're looking at cosine. So let's use that one. We've got cosine of 52.5 degrees equals adjacent over hypotenuse. If I solve for A equals 14.2 times cosine of 52.5 degrees. Cosine of 52.5. I've got A equals 14.2 times 0.608761429. And I'm going to multiply that by 14.2. A equals 8.644412292. How many significant digits did I have? 3. That's got 4. We're going to assume since they gave it this, it's 4. But the 0, maybe 4, 3, we don't know. We actually do know. It's 4. Because if it wasn't 4, they would have used seconds. We're going to use the smaller one, so we only want 3 significant digits. 8.64, and the units were inches. All right. Finally, what else do we want to do? What else can we do? Well, we got a couple ways we could find B. That's the one we got to find still, right? Oh, wait. Let me make sure you got it written down. Pause it if you need to. We still need to find B. How can we do that? Well, B is the opposite, and we have the hypotenuse. So side B, use sine B, or a squared plus b squared equals c squared. I'm going to use sine B because this is trigonometry. Let's use that. So I've got sine of B equals opposite over hypotenuse. Sine of 52.5 degrees equals opposite, which is side B over 14.2 inches. So B is 14.2 inches times sine of 52.5. Throw that into a calculator. You don't have to do it in steps like I did last time. I can do it all at once. 14.2 times sine of 52.5. Make sure you're in degrees, not radians. My little thing, you can't see it's a D. And I get 11.26561743. We're going to 3 significant digits. Those 3, we look to the number to the right. Do we round up or not? 5 or greater, we round up. So B equals 11.3 inches. And we're done. We have all this measurements. All right. Let me give you guys one to try. So your example, I just want you to pause it and work through it. You are given side B equals 19.32 centimeters. Side C is 36.12 centimeters. And angle C is a right angle. It's 90 degrees. All right. Pause it. Try to work through this. Find side A and angles A and B. All right. I'm going to write those in here. That's stuff to fill in. Finding side A is probably the easiest thing to do. Let's start off with A squared plus B squared equals C squared. We have A squared plus 19.32 centimeters squared equals 36.12 centimeters squared. You throw that in a calculator, you get 375.1969 centimeters squared. And on the right side, we have 1,304.6544 centimeters squared. Don't dump all the decimal places now. You only do the rounding for significant digits at the end. We'll subtract that over. A squared is 929.4575 centimeters squared. Take the square root. We're going for the positive root. And I get 30.48700,543. The square root of centimeters squared is centimeters. It's good to put the units in there because if you have different units, it'll let you know right away. Like if we had centimeters and meters, they don't mix. We have to convert. So it's good to have them in there. And on our sides, we had 4 significant digits. That says round up. 30.49 centimeters. All right. Before I continue, I'm going to draw the triangle just so I can see what's going on. It's easier to keep track of stuff. C was 36.12. I'm going to label angle A and B because that helps me choose where side A and side B go. That matters because we have to use the trig functions to find the other two parts. So if I want to find angle A, I've got some options. I got all sorts of options. I could do sine, cosine, or tangent because I have all 3 sides. Which one should I use? Use the one that has the most starting information. Because I rounded A. I know A is rounded. In fact, I'm going to put a little X there to remind me that that's rounded. You could put a check mark or something, a little wavy line. A is rounded, so I want to use these other 2. So for side A, angle A, I have adjacent and I have hypotenuse. Adjacent is 19.32 centimeters. Hypotenuse is 36.12 centimeters. Adjacent and hypotenuse lead to cosine. Cosine of A is 19.32 centimeters over 36.12 centimeters. All right. Notice centimeters cancel out. And what we have to do, we have to use that inverse thing we were talking about earlier. This is A equals cosine inverse of 19.32 over 36.12. Notice centimeters cancel. This is just a number. So I can do it all at once. Shift cosine inverse. I got to do parentheses. 19.32 divided by 36.12. A is 57.663974 degrees. And the only actual numbers we were given were all 4 significant digits. So we're going to use 4. We look to the right, it says round down. So A is 57.66 degrees. If you don't do it all at once, you got to make sure you do not write down stuff and copy it in. So I'm going to do the 19.32 divided by 36.12. Now, even I could write that down and put it in as cosine inverse, but I'm sure there's numbers after the 2 that are not being shown here. So instead, I'm going to say shift cosine inverse. I'm just going to tell it to use the answer. Okay. Angle B, what can we do? I'm going to put a box around that. I'm going to write it up here in my table. Angle B, well, this would be opposite and this would be hypotenuse. I could use sine, but why? A and B are complementary angles. They add to 90 degrees. So therefore, A equals 90 minus B. Or B equals 90 minus A. The latter one's more useful here. B equals 90 minus 57.66, which is 32.34 degrees. And ta-da! All done. All right. You guys ready for more? So, general pro tips, word problems. Word problems tends to mean real life problems. Usually those are what they use. Word problems, Dave's pro tips or El Jefe's pro tips. Not pro trips, pro tips. Number 1, draw a picture. They help. And the reason why is often you can gather extra information that wasn't necessarily given to you. That wasn't given. Sometimes you can just see it and you can reason it out. When you're doing this, when you're drawing it, label with given info. And anything not labeled should be given a variable. Now, or maybe we should throw an S in there because usually there's more than one. A, B, C, X, Y, Z. Hell, you can use smiley face, frowny face, and crazy face. Those are variables. As long as you identify them as variables, they're variables. I've used smiley face on an exam. When I was taking trigonometry at College of the Sequoias, I got tired of using X and Y after doing algebra for so long. I threw smiley face in. I said smiley face represents this side. And the teacher asked me what the hell was wrong with me, but I got full credit because I identified it as the variable. Once you have that picture, use the sketch to come up with equation or equations that relate the given values with the variables. That's what I just did in that last picture. I said, what pieces of information do I have? Does this meet, this is trigonometry. I have sine, cosine, tangent at my toolbox. Which one works? The one I have information for was cosine, so I used cosine. And I pulled that directly from the picture. Finally, solve the equations. And make sure the solutions make sense. For example, remember that 12 by 10 box I had? If I found the diagonal to be 8.73 feet, does that make sense? $12 feet here, 10 feet here. How could this side be shorter than the 12 feet or the 10 feet? No. Doesn't make sense. So I messed up somewhere in my calculation if I got that. If it's too big, if I got 8,000 feet, clearly something happened. There's no way the diagonal is 8,000 feet. Okay? So let's look at some more examples. Pause that, let you write it down if you need it. Okay, the following bit requires me to give you some more terminology. So let's tell you what angles of elevation and depression are. And this is not depression like I feel miserable depression. This is going up or down. So let's say you're on a building. Here you are, you're right here. You're like, yay, I'm king of the world. But you're not. There's a taller building over here. And let's say this is ground level since flat ground. And I'm just going to shade these in a little bit to illustrate that these are solid objects. So what we do, I draw a straight line going over, and then I can draw a line going from that corner down to that corner, and that corner to that corner. I'm going to call this A, angle A, and I'm going to call this angle D. Angle A is the angle of elevation. Angle D is the angle of depression. So that's how that kind of stuff works. Let's do some word problems with it and work through the word problem solving process. So, example. A flying squirrel. Yeah, let's do it. A flying squirrel glides from a 40.0 foot tall tree branch. It's on a branch on the tree, not the top, to the ground where, let's make it a she, where she lands 93.6 feet away. What is the angle of depression of her flight? So that's our question. Give you a second to write it down. Pause it if you need to write down the question. All right, I'm going to draw me a picture. So here we go. This is my tree. Isn't that a great tree? And there's a branch sticking out right here. It's a long one. I'm making it longer. And here's my little squirrel right here. Woo! That's my squirrel. And this is the ground. And she jumps off. And well, that doesn't look very flat, does it? She lands. And if I go straight down, the distance from here to here is 93.6 feet. Her starting branch was 40.0 feet up. What's the angle of depression? Now, I could try to make a little rectangle here and go, what are we working with here? Well, if we look at our picture up here, that's what we want. So, hell, I'm going to use smiley face. Let's use smiley face. That's angle smiley face. Now, I got a couple options. I can recognize that this is a right angle, and I could find angle A, and then subtract angle A from 90. So smiley face angle equals 90 minus angle A. That's one option. That means I have to calculate A and then calculate smiley face, which isn't a hard problem at that point. The other option I have is to recognize if I made this rectangle, sides opposite sides are equal length. This is 40.0 feet, and this is 93.6 feet. That would make this it's a rectangle, so that's a right angle. This is my hypotenuse. What pieces of information do I have for smiley face? We have 3 choices. SOHCAHTOA. I do not have hypotenuse. So the ones with H's are out. I can do tangent. So let's do tangent. Tangent of smiley face equals opposite 40.0 feet over 93.6 feet, which is adjacent. Feet cancel, and if I do the inverse, smiley face equals tangent inverse of 40.0 over 93.6. Parentheses. Put down here where you can see it. 40.0 divided by 93.6. Ooh, I said 0.6. That's still not 0.6. There we go. 40.0 divided by 93.6 equals. So smiley face equals 23.13946.176. It was in terms of angles, so it's a degree. And how many significant digits do we have? We had 3 on each of them. So smiley face, we look at the first 3, we round using the 4th one. The 3 says round down, so it's going to be 23.1 degrees. All right. All right, some more examples where this pops up. Navigation. You'll hear the term bearing. Not like bearing children, but bearing is like heading. It's a term in navigation used to describe the direction being traveled or heading. They also call it heading. And the way it's usually given is this. It's a single angle, and it goes different than when the way we're going to do most of the time. Most of the time, we start on the right and go counterclockwise from the x-axis. This is clockwise from north. And so you want to make a picture. So if I've got a heading going north and I want to go bearing 115 degrees, I go clockwise. This would be 90. And I need to go 90 to 115 is another 25 more, maybe that much. So that would be 115 degrees. This is the bearing or direction being traveled. That's when you have a single piece of information. And the other ways they do it is they will give 2 coordinates, 2 directions. So option B, they give 2 directions. And you'll see what I mean when I do the example. We are going to start with a north-south line. Then it will gives an angle. Towards east or west. So if you're not familiar with the compass, it's time to get so. North is up, south is down, west is east, west is left, west is east. That way to go, Dave. West is left, east is right. So, for example, these are the kind of things they'll give you. They'll say north 57 degrees east. What they want you to do is start at a north bearing, rotate 57 degrees in the eastward direction towards E. And that's the heading right there. And they could do west, north 25 degrees west. We start north. We rotate 25 degrees towards the west. And that's our heading or bearing. They could go south. So south 32 degrees east. We start off heading south. We rotate in the eastward direction 32 degrees. That's our heading. So this is 25 degrees, 32 degrees. And if they do south towards the west, south 62 degrees west. You start off heading south. You rotate 62 degrees. And towards the west, and that's your new heading. So that's the kind of things they do. Got a fun problem, a couple fun problems for you. I want to make sure you got this written down and you have some understanding of it. All right. So we've got the first example. These are problems similar to what they'll ask you in the homework. This is why I'm going to do some. 2 radar stations at point A and B are 5.3 miles apart on an east-west line. They're directly left and right of each other. They simultaneously detect a plane. Station A detects it. And we'll say the plane is at point C. With a bearing of 57 degrees. Station B's bearing is 327 degrees. Find the distance the plane is from station A. Okay. So I'm going to draw a picture. We know that station A and B are on an east-west line. I'll start off with A. I'll put A down. We're doing bearings, so we got to go off of true north. 57 degrees is about like that. 327 degrees is pretty steep. We'll say that's B. That's north there. So this was 57 degrees. 327 degrees is all the way around. This would be 270. That's about 327. And I'm going to extend those till they cross. That's point C. And my little plane is right there. It's got wings sticking out. Maybe it's a jet plane. All right, so what do we got a triangle here, right? What could we use that would help? Well, let's look at the triangle. What are these angles? Let's call this, we've already used A, B, and C. Let's call this angle D, and let's call this angle F. So we know that from true north to east is 90 degrees. So 57 degrees plus D has to equal 90 degrees. We subtract 57 degrees from the left side, we get 33 degrees. We know if we go all the way around, this is to 270 right here. So 270 plus F has to equal 327 degrees. We'll subtract 270. And I get F equals, what is that, 53 degrees? Oh, no, I'm sorry, 57 degrees? Yeah. Yeah, that's 57 degrees. Okay. So that's 57 degrees. What do D and F add up to? So what's angle C? D plus F plus C equal 180. We've got 33 plus 57 plus C equals 180. 33 plus 57 is 90. So C equals 90 degrees. This is a right triangle, which means we can use the tools we have. If it wasn't a right triangle, we got to wait till like chapter 7 or 8. So what are we looking for here? I'm going to redraw this triangle. What else did we have? This was 5.3 miles. I'm going to sketch this triangle. I'm just going to rotate it like this. So this is C. That's point A. That's point B. This is 33 degrees, 57 degrees, 5.3 miles. And I want what side? I'm looking for the side right here, which is this side right here. So let's call that X. What do we have? We have the hypotenuse. So I can either do sine using x because it's opposite, or cosine using a. Sine of 57 degrees equals x over 5.3 miles, which is also equal to cosine of 33 degrees, whichever one you want to use. Let's use the sine. Why not? Let's do sine. I'll multiply through by 5.3. X equals 5.3 miles times the sine of 57 degrees. .3 times sine of 57. 4.444. $95401. It looks like we've only got two significant digits. The 5.3. We look at the 4, it says round down. X equals 4.4 miles. If you had done cosine, this would have said 5.3 times cosine of 33. And let's just make sure we get the same thing. Same measurement. Cool stuff, right? All right. Let you finish writing that down. We got two more examples that we'll be done with this lesson. That one had bearing. Let's do one that has the two pieces of direction. So let's say a drone, let's say they built Amazon in Fresno. A drone leaves Amazon in Fresno. To deliver a package. But it can't fly in a straight line because the airport's in the way. But it must go around the airport. So first off, it flies. It starts flying. And all of it is at 30 miles per hour. It starts flying with a bearing of south 40 degrees west. And it goes that direction for 10 minutes. And then changes direction to north 50 degrees west for 20 minutes. At which point it drops the package. How far is the drone from the warehouse? Assume that's where it started from. Okay, so that's our problem. So we've got a couple things. Maybe we should figure out how long each of those legs are. First off, we've got a speed, we've got a time. Speed given, time given. We can calculate distance. So, for example, speed is distance over time. So what do we have? It flies 30 miles an hour. Which means it's doing, how much of that is it per minute? Miles in 1 hour. We want to get rid of hours and put in seconds or minutes, 60 minutes. Hours cancel. 30 over 60 miles per minute is 0.5 miles per minute. So part A, or leg 1, the first part it does. If I solve for distance here, D equals S times T. So D is 0.5 miles per minute. And it has to fly for 10 minutes. The minutes cancel as we wanted. 10 times 0.5 is 5. Leg 1 is 5 miles. We do leg 2. It flew for 20 minutes. This is going to be the same thing, but twice as far. 0.5 miles per minute times 20 minutes. Minutes cancel, and we're left with 10 miles. 20 times a half is 10. Okay, now we've got that. Let's draw a picture. So here's our warehouse. A for Amazon. And it starts off, it starts off with the south 40 degrees west bearing. It goes 5 miles that way. Let's say that's 5. And then from there, it goes north 50 degrees west. That's a north-south axis. I rotate 50 degrees from there. And it goes twice as far. So it goes that way, and then it goes that way. And this is its destination. We want to know that distance right there. Let's call it X. I'm betting if there's a 90-degree angle, it's right there just by the picture, but we can verify that. I'm going to do this part right here. I'm going to blow it up over here. We have angle A is doing that. This is 40 degrees. Let's make a rectangle. That makes this 50 degrees because it's a right triangle. Or right angle. 50, this is 90. That's got to make that 40. In fact, these are called alternate interior angles. When you have two parallel lines and they're bisected by an angle, we'll do this more later on. This angle matches that angle, and it matches that angle, and it matches that angle. And the other ones match too. It's kind of neat, right? It's a little bit of geometry for you. So that means this angle right here is 40 degrees. And we already knew this was 50. That was given to us. So that does 50 plus 40 makes that a right triangle. So we've got a right triangle. And I didn't finish labeling it. That was 5. This was 10. Okay. I'm going to leave that there. I'm going to just give myself some room. I'm going to rotate that picture. I got my right angles down there. And on the bottom side was A. So that was the warehouse, which makes that the 5 and that the 10. What are these angles? Do we need it? Let's call it F and G. Do we need angle F and G? And or angle G? Well, what was the original question? How far is the drone from the warehouse? What we're looking for is X, which was right here. We even labeled it on this picture. I don't actually need F or G, do I? Why not? This is a right triangle, and I can use A squared plus B squared equals C squared. 5 squared plus 10 squared equals X squared. So 25 plus 100 equals X squared. X squared equals 125. X is the square root of 125. And that is, how many decimal places did we get? The original problem was rounded to the whole mile. Depending on what you're doing this for, your answer could be X equals 11. Or if they actually wanted more precision, they said it was 5.00, 10.00. We could say that was, if we rounded the first decimal place, 11.2 miles or 11.18 miles. After that, no one uses too many more decimal places than that. All right, so let's do another example. I'll do it on this page. We'll get the artwork in here and we'll do the work on the next page. So let's see, Alejandro's a pimp ass name. Sounds like Don Juan. Alejandro is trying to determine the height of a flagpole. Without climbing it. He doesn't want to go up it. So he stands a short distance from it. Where the angle of elevation of 43.2 degrees to the top of the flagpole. I might not be able to get it all on this page. We might have to do the art on the next one. He backs up 60 feet. Let's say exactly 60 feet. And has a new angle of elevation of 28.2 degrees. Find the height of the flagpole to the nearest foot. Yeah, we're going to need another page for that picture. So I'll let you guys process that for a second, write it down. We'll start doing a picture. Okay. So what do we have here? There's a flagpole here. And let's say there's a flag waving from the top. We've got our good old red, white, and blue in there. And the ground is flat. And Alejandro starts off at a distance from it. And to the top, it makes 43.2 degrees. He backs up 60 feet. I don't know how far that is relative to where we got. Let's say this distance is 60 feet. And we make a new angle of elevation. And this is 28.2 degrees. Our objective is to find H. H. Okay? That's all the given pieces of information they gave us. So this is what we got. What are we missing? Well, we don't know how far he started from the pole. Let's call that X. This distance right here will be X. And we don't know the hypotenuse. Let's call this D. Don't know if we need it. Don't even know if we need this one. Let's call this length here F. We don't know that one either. So that's what we got. Flagpole is vertical. We know that's a right angle. That we also have that. Okay. So we got triangle. We got a couple triangles, don't we? We got two triangles. I got a big triangle that's kind of flatter. And this is 28.2. This is H. And this is X plus 60 feet. And I also have another triangle. 43.2. This is X and this is H. So we've got two triangles. And it's the same flagpole, so those are the same. That's important to know. So what kind of thing can we, let's call this triangle 1 and 2. Let's make it a picture of a triangle. Triangle 1, triangle 2. Triangle 1, what trig function could we use? We know this is the right angle. This is the hypotenuse. So we're looking for the opposite side, and we have a piece of information about the adjacent side. We could use tangent, right? So Katoa, we have opposite and adjacent information. tangent of 28.2 equals opposite, which is h, over x plus 60. We look at triangle 2, we have the same function, right? It's tangent. And this is h over x. And what are we trying to find? We want to find h, right? So keep that in mind. That's our end game. That's what we want. We know these h's are equal. Let's get rid of fractions. Let's clear fractions. If I clear fractions on the left, I'm going to move the h to the left. I've got h equals x plus 60 times tangent of 28.2. And here I have, I'm going to leave it on the right here, h equals x times tangent of 43.2. And the reason why I wrote it like this is because I know these h's are equal, which means these two things have to be equal, which means those are equal. Let's work with that. So I'm going to distribute. I've got x tangent of 28.2 plus 60 tangent of 28.2 equals x tangent of 43.2. And I want to solve for x, and then I can find h. So what I'm going to do is I'll get all my x's on one side. The side opposite where the constant is. And I get 60 tangent 28.2 equals x tangent of 43.2 minus x tangent of 28.2. I'll pause, let you get caught up there. We're going to need another page. The next step is stuff a lot of people that are doing algebra aren't necessarily comfortable with. They're used to distributing, but not really doing factoring like this. We can pull out that x. I've got 60 tangent of 28.2 equals x times tangent of 43.2 minus tangent of 28.2. And then I'll divide by that. And I get x equals 60 tangent 28.2 over tangent of 43.2 minus tangent of 28.2. Okay. If I do that right now, I'm going to get a number that's going to have decimals in it, and I'm going to have to round. This is not what I want, though. I didn't want x. I want h. So we go back up here to what we had. I'll use this one right here. H equals x times tangent of 43.2. And that x is that x. Let's plug it in. A lot of writing right there, right? The reason why I did that is I've shown my work with complete accuracy. I have made no assumptions or rounding or done anything right here. This is the exact answer. Not really helpful. So now I'll calculate now and round. So I've got 60 times tangent of 28.2 times tangent of 43.2, because this is like a fraction. I can multiply that in on a numerator. And then I can say divided by parentheses tangent of 43.2 minus tangent of 28.2. I'll end the parentheses. And now I've done everything all at once in the calculator. I've made no rounding errors. Whatever I get, I get. H equals 74.9906001. This was in feet, right? Yeah, Alejandro was in America. He was measuring in feet. It said round to the nearest foot. H equals 75 feet. It's a good size flagpole. Okay. That's it. That's all we got. If you want to see more like that, come hit me up in office hours. I can throw another couple at you and do them with you. But it's a long problem, and I don't want to make the video longer than I need to. So that's the idea of how to do those problems. We had a couple triangles, couple equations. This was a good 2.5 pages of work. I'm writing kind of big, though, so I can present and stuff like that. But still, it's a lot of work, right? But it's kind of realistic. Who wants to climb a 75-foot tall flagpole? There's no handholds on that bad boy. You'd have to shimmy up it like a tree climber, but no branches. All right, that's it for 5.4. That actually ends chapter 5. Next section, chapter 6, is on radians. We'll get started on that shortly. Peace. And end.